Starting.
All right, guys, go ahead.
So, hello. Yeah.
Yeah, as you start talking, the camera will pick up your voice and go to you.
Hey guys, how are you doing? Good to see you.
So, where do we want to start off? We can start with the slideshow if you want. We have a little presentation made for things. I do apologize in advance for all of my sketches where you cannot read my handwriting, but
That's okay. Introduce yourselves and tell us what grade you are and maybe what you want to do after Harley school.
sure. I'm Charles Solge. I'm a senior this year, so I'm graduating, and I want to go into physics and astronomy in college.
Awesome.
I'm Danny. I'm also senior at Harley, and I want to go into physics, and I'm not sure if something else.
Okay.
Awesome.
My degree is in physics, and there's so many different things you can do with it. So that's excellent. All right. Tell us about your project.
So we are doing the lunar supply pod garage. We focused a lot of our research on like dust prevention mechanisms, preventing air leakage and sealing, stuff like that. But we also have a basic design for the habitat overall, which we will share with you, I believe, on the first slide of our presentation. I'm not sure if it's shared yet.
There's somebody missing, Siam.
Siam has not been here for the last couple meetings, so he elected not to come to the presentation because he felt he didn't know enough about what we had been doing recently.
Okay. All right. Keep going. Tell us more.
Yeah. We see your PowerPoint.
All right.
Perfect.
Can you go to the first slide? All right. So the basic design of our habitats, we designed it to be an inflatable habitat that is always designed to keep its shape and structure. So the interior of the garage itself can be pressurized or depressurized as necessary, but there will always be like a second layer of permanently inflated things to keep a layer of lunar regolith as an outer shell, just to keep away radiation and insulation, things like that. As you can see on the left side, we're attached to the airlock. I get into details of how we attach to the main lunar habitat in a later slide, but that will be at that point that will attach. Going over to the right side, we designed a multi-zipper airlock system. We decided to go for a zipper airlock for the hatch on the side of the garage, just to make it wide enough to not only be able to bring in supply pods, but also the rover for necessary repairs and maintenance. The garage itself should be big enough to fit multiple supply pods at a time, as well as the rover. So we don't have the exact specifications of the rover, but on the right side you can see there's a ramp like that. That will be a little bit wider than the widest thing that we'll bring up to habitat, which will likely be the rover itself. So the ramp in the side, once again, we'll go into more detail in a later slide, but you can see there's a flat area at the top next to the hatch, as well as a lower area. So that flat area is raised up above the surface. This is to make it easier to clean dust off the things outside of the habitat, and to ensure that any dust that does get on can be effectively swept off the side of the ramp. Next slide.
Good.
Okay. So first thing, how it's going to be delivered and attached to the main habitat. Because it's an inflatable airlock and it's made of soft materials, it can easily be rolled up and compressed. It can simply be unrolled on the surface, inflated, and then have regolith built on top of it afterwards. For how we attach it to the existing habitat, we had a couple options in mind. One we wanted to discuss with you. One of them is using a similar method to how we create the zipper hatch initially, to make an airtight zipper and effectively zipper on the garage itself. Put like one side of the zipper on the initial habitat and the other side on the lunar supply pod garage, and just seal them like that on the surface. Another option is if there's space for it, a rigid attachment to make it more secure. Airlock attachment that will fit nicely onto the habitat itself. The other thing is that we intend to produce the other side of the garage, the ramp, on the moon, because it's a large rigid area, but it doesn't need to be made out of specific materials. It could be made of regolith concrete and or aluminum processed on the moon. So this is an opportunity to use construction materials found on site rather than shipping more stuff up. Next slide. Talking about that, the ramp and cleaning area that we have leading up to it, if it looks a little bit like this is of course not to scale. It would be wider than this to fit the lunar rover up to the top, but it should, the rover or the crane mechanism will be able to deliver the supply pods directly onto that flat area at the top there, either rolling up the back of the ramp and depositing them, or rolling them up the ramp if the astronauts choose to. From there, on that platform, we'll go through our dust removal procedure. This is to get the majority of the dust off of the supply pods and off of the things that we're bringing to the habitat before they actually enter, just to prevent as much contamination as possible before it gets inside. We'll do this, I believe.
Sure. So we first want to get rid of the visible dust that can just be swept off. This is just the majority of visible stuff if it's able to be swept. And but for stuff that sticks to the surface of supply pods or of a rover, one thing we wanted to know is if an electron beam could be used to levitate them off. We saw that that electron beams were used successfully to remove dust from the surface of objects, and since they can be projected in a cone, we were wondering if it would be safe or feasible to use that to perhaps clean stuff before it enters the garage.
I think there's possibilities with that. I haven't done that myself, so I can't answer a whole lot. But let's see. If you do a Google search of lunar dust remediation or something like that, I think what you'll find is that there are some electronic methods to be able to remove the dust, and which ones would work best for this, I don't know, but I know that there is research being done on it. Okay.
And we have Cody here also. Cody, you have any comment about that?
No, just to echo what Glenn mentioned, there are some ways to do it. Make sure you do some research to figure out how it works. One negative to using the electron beam to get rid of dust is that it does charge the rest of the environment. So if you think about removing all the dust that you can, that's great, but then you essentially have a net negative or net positive charge on your suit or the area that you're working in. So something to think about. Normally, those type of environments or facts are available when you research the dust mitigation by electron beam. So I think there's some good stuff out there.
Thank you.
So does that mean that bald guys have it easier just because they don't have to worry about the frizzy hair thing?
Yes, correct.
Okay.
Mr. Johnson, we could just get a little comment of this, but this two-step approach of first, getting as much off as you can see outside, and then moving on to the final kind of definitive step. Does that hold water for you?
Yeah.
Yes. I would imagine that it seems like there would be value to having some kind of a brush that knocks off a very large portion, and then maybe some kind of an electronic method for more. But, I haven't done it, but it seems like that would help a lot. Now, the Apollo astronauts also had some kind of brushes, right? And so you might look up and see if you can find information about what they had used, because I do know that they used some brushes. I suspect they were like a horsehair brush, but I'm not positive. I'm not positive on that.
Take the one out of my trunk that I've been using for a while.
Well, and I bet if you look, you might be able to find some pictures. They looked similar to what you might use on your car, just to brush off the snow.
Okay.
Next slide, yeah.
Yep.
So this is going more into depth on our actual hatch system for the zippers. So our idea was to use multiple separate zipper hatch layers effectively to create, for a lot of reasons. One of which being reducing air loss. By having multiple separate zones within the airlock at multiple different pressures, any slight holes or gaps in the zippers will lose much less air over time than if the entire airlock was pressurized, in fact, 100% on one side, 0% on the other. By having multiple layers like this and multiple vents inside each of those layers, we can not only monitor what the pressure is at inside the habitat or inside the airlocks at all times, we can adjust it if necessary and easily discover leaks or anything like that. This also will make sure that even if there is a leak, that the hatch doesn't immediately rupture, things like that. It adds a bit of redundancy. Each of these layers separately should be able to withstand the full 100 to 0 pressure gradient from one side to the other, but it'll separately reduce wear and tear over time because there'll be less pressure on each individual section of the layer hatch. On the hatches themselves, something we were worried about was dust getting inside the zippers or getting inside the zipper lines. So we have taken a couple steps to prevent this from happening. Number one is having the actual fabric roll up to the top. So roll upwards away from the ground. So while supply pods are rolling in, that dust will naturally shake down towards the ground away from where our zippers are, things like that. And we can roll it over the hatches on the bottom. Other idea was, once again, use electronic mechanisms, electrostatic dust shielding. We know there's methods of repelling dust from certain areas using dust shields. So our idea was to, around like the zipper lines themselves, place a line of this repulsion to repel the dust away from those lines, especially worried about the bottom and like where the actual area that the supply pods and rover will be rolling over. We're worried about dust contaminating that area. So using electronic methods to repel dust from there, as well as the more simple method of putting a tarp over it temporarily, just as they roll the supply pods over the bottom like zipper teeth, then just covering it with the tarp temporarily and bringing it back inside or bearing it back outside and cleaning it afterwards.
Sorry, was that next?
Yes.
Yeah, sorry.
No, yeah, go ahead.
And so for removing dust, we had some ideas like the electron beam thing. We found that was called the moon duster. Tools for supply pod, depending on how much of a problem it is, you could removal using like the electron beam or hover technology, removal of dust, just in the spot where the supply pod will be opened, to get dust off of that area so that it's not contaminating whoever's opening it. We have removal outside of the habitat where majority of the dust will be removed generally. Once things are brought into the garage, we found that gravity actually takes out or removes a lot of the dust particles from the air. They settle down to the floor over time. The pressure shouldn't make a large difference for this. The pressure of a garage, mainly it takes around 30 hours for this dust to settle, but the gravity could be a very useful tool for getting rid of the large majority of dust because it can easily be vacuumed or swept off the floor. And a HEPA air filter is also something to remove the last remaining dust from the air because that will filter out. It's been shown from some NASA reports to be very effective in removing the fine particles of dust that remain airborne.
Yeah, the HEPA filter would be kind of the last thing to do. Most of the dust, as we were saying, is removed by gravity over time. The pressurization of the habitat, whether it's pressurized or not, doesn't make a large difference. I believe it was like 23 or 24 hours versus 30 hours with or without atmosphere. But especially because we can keep the habitat at a lower pressure overall. We can keep the garage at a lower than atmospheric pressure. So the dust should settle relatively quickly over time. Bringing the procedure for this would be to bring multiple supply pods in at a time, let the dust settle, vacuum it all up, let the air filters take care of the rest, and then bring in the materials.
One other thing with the air filters we found was that they tend to accumulate dust in them relatively quickly and can't be cleaned from the filters. So minimizing the amount of dust that filters have to filter is really important for maintaining their lifespan.
Is that it?
I believe that's it.
Okay, I'm going to unshare here so we get a hang on. How do I stop share? I know how to stop share. It's a big red button. There we go.
Okay. All right. I like some of your ideas here. Have you guys started assembling anything to be able to share with?
No, we haven't started working on the actual model yet. We wanted to see if you guys had any saw any glaring problems with our ideas or things like that before actually starting to put stuff together.
Okay. Well, and it's always helpful to have something in front of you to be able to point at.
I do
So
have the sketches.
yeah, I've seen your sketches. That's okay. So one question I've got for you is, in terms of size. So as you're designing this, how the bigger it is, the harder it's going to be to get it to the moon. And so we have to look for ways to design it as big as you can, but still within the transportable capability, right? And so having the idea of having multiple supply pods in there, that sounds terrific, but I'm not sure how big of a structure we're going to be able to have. So keep that in mind. And so as you're putting together your prototype, you want to see if you can come up with scaled objects. So I gave you like the size of a baseball as being the size of the supply pod. Do you have like Legos so that you can build some kind of a rover that would fit that kind of scale and then be able to have people so that you could get an idea of it? Is that something possible for you guys?
Absolutely.
Okay. And then what would you make your prototype out of? Have you been thinking about that?
No, we haven't moved on to that stage of our project yet.
Okay. And so, I mean, you're talking about an inflatable. Do you guys have some sewing capability or somebody that can help you sew, to be able to show, this is how big it would, it starts off like this, and then we inflate it, and it starts getting to be this size, and then be able to show that kind of relationship. Does that make sense?
Yes.
Yeah, just as a skill model. Don't build the whole size of your garage. Just make a skill model for that. And
Now,
the other thing I was worried about, because you want our opinion, is the zippers. I really appreciate how you mitigated the dust, right? You took extreme caution. You have redundancy. It's wonderful. I have no problem with that. And I've seen really watertight zippers even that, they make pouches that are watertight. My husband has one because he puts his cell phone in it when he goes fishing and he always lands in the water. But how are the astronauts with their gloves on outside their habitat going to manipulate a little zipper? They can, but you gotta design that end of that zipper with a big, this zipper,
like
this zipper only has a little thing, but if you had like a baseball on it, then they could manipulate it. So don't forget about that zipper and the astronauts with their big gloves on. Have you thought of that?
Yeah, I mean, that was my area of the project. So yeah, I did think about that when we were designing the zippers. I didn't mention it in the presentation, but ideally, at least the tabs of the zippers would be scaled up to fit in an astronaut's gloves of a spacesuit. So
very good.
Obviously, the zipper itself could be scaled up or scaled down as necessary, but as long as they have a tab or something to grab onto, then they can drag the zipper from that.
As long as the zipper piece itself never breaks, it's really, even if a handles for whatever reason breaks off, it's really easy to, with a pair of pliers and a small metal wire, to just repair or replace the connection between the handle and the zipper itself.
Right, make your own, right? Which would be cool. And it doesn't have to be a hard, made from like a hard sub. It could be a strap that they can put their hand in and pull it down, and that strap collapses, you know. So just think. I like how you're thinking creatively. Think outside the box.
Cody, you got any thoughts?
One thought in conjunction with the zipper, the multi-zipper approach, make sure that there are technologies or zipper sealing methods available that can deal with the delta pressures from each side. So the quote unquote airtight zippers that I've seen are usually good for one torr or one atmosphere, or one torr or one atmosphere. Those are not the same. But just make sure that you're not having too much of a pressure differential on either side of your airtight zipper, because it won't seal. It looks like you're pretty close to figuring that out. Just a word of caution as you work through those.
And what about temperature? The zippers have to be able to withstand the plus and minus 250 degrees Fahrenheit.
Yes.
Yeah, that's actually a really good comment. That's I don't know of zippers that have been tested to that extreme, so it's worth looking into.
Yep. Now, so follow on, the external zipper would have to deal with those temperature extremes. It is possible that as you went closer and closer to your conditioned volume, it would be less and less of a temperature extreme. But
Sure.
to be safe, you would want to design them all to the same temperature extreme. So metals are usually tough for something like that. Aluminum is out, because it just has such a coefficient of thermal expansion that it'll change its properties immensely as you go from hot to cold and vice versa.
So what do you think, Cody, about zippers?
I like them.
I like it too. Glenn, what do you think?
No, I think for this application, it's going to be tough. To have a seal and to keep it with a zipper mechanism is going to be really difficult. But do some research, or continue to do the research. Look at some of the applications in space for sealing. Maybe there's a good application that you can reference for a zipper-based approach for some of this. But I think that there are going to be some challenges with the zipper approach.
So do we use zippers on the spacesuits at all?
Yeah.
Yes. So we do use them in the spacesuits, but normally they're part of a multi-sealing type approach where the internal garment is zipper based, and then there's rigid rings that go around from the different joints. So I don't know if we've ever used it as a primary sealing method, but I could be wrong. I'm not a spacesuit engineer type person, but yeah.
Well, and one of the difficulties is that our current spacesuits don't have to operate where there's dust. And so that is probably our biggest, one of our bigger difficulties with those, with any kind of zipper, is just we haven't done it a lot. The Apollo astronaut spacesuits did have zippers, but exactly how they were used, I don't have firsthand knowledge on that. So it might be worth looking up to see how they used how their suits were configured. So that'll be something interesting.
Yep.
To go back on some of these other so for example, your ramp going up, I like that idea. I think that having a ramp with holes in it so that a lot of your dirt falls off just from going up and bouncing around on it, I think is a great idea. One thing I didn't hear was, how were you planning to attach to the porch? So here you've talked about the garage, you've talked about the ceiling hatches or the ceiling zippers on the front side, but of course you also want to try to show us how are you going to attach to the porch the airlock that is already on the habitat. And just to be aware, right, it already has an indoor, an inside hatch and an outside hatch. So really, you just need to be able to demonstrate how you want to attach to that airlock so that you still have a good seal and be able to use that airlock. Does that make sense?
Yeah, I thought we had addressed that at the start. I could be
Well,
wrong.
maybe you did and I missed it.
Well, but I think he just wants a little more specificity. You have it drawn in that it would do that, but a little more specificity exactly how those would interdigitate.
Yeah.
Make sure that's specific.
And just be able to give us a little bit of plan of how you plan to attach, okay? Because you can imagine that that's going to be a critical attachment point as well, okay?
Perfect. And we're about winding up on our time. Any last?
Okay.
I want you guys to. I've been one of the later presentations on these in years past, where they've been. Everybody runs 5 minutes late. The next thing you know, you're 30 minutes. I don't want to be that guy to leave things off and be behind. But any last, as we used to say in the Marine Corps, saved rounds of things you can say?
Do you guys have any questions for us?
I first. Go first. Sure.
Mine might be.
No, you go first.
Okay, sure. So I just wanted to ask, based on what we presented to you today, is there anything that we overlooked in the direction we should be exploring for the presentation, or we should be considering, I guess?
I didn't see anything so much overlooked. I think that you're going to encounter, different complications as you start assembling something in front of you. As soon as you start building some of these things, you're going to say, oh, did we think of these things? Did we think of that? And that's when once you have something in your hands, both of you can point and say, we need more of this and less of that. And I think that you're going to have some revelations as you're traveling along that first path.
Mm-hmm. And don't start by 3D printing. Start with your drawings, which you've done. Now go to cardboard or material that's easily found around. You have a really good shop there, kind of a maker space in the back of your classroom. Use the stuff, make a model, a skill model, and last, if you're using any 3D printing, do that.
All right. Well, thanks, team. We appreciate your time very much. I will see at least you tomorrow. One more presentation.
Sounds terrific.
Yep. Keep up the good work and have a wonderful afternoon there.
All right. Well, thanks for all the feedback, team.
Yep.
Thank you.
All right.
Thank you.
Bye-bye.
Have a good afternoon.
Forgot a hat.
Oh, at least I remembered to record.
Okay.
All right, so Glenelg is up.
Excellent.
Glenelg and then Olympia.
Hello.
Hi. Thank you for your patience.
Yeah.
I appreciate that. So introduce yourselves. Tell us your name and grade and what you want to do once you're out of that wonderful high school.
Yeah. So my name is Jonathan Polanski. I'm a senior, and after high school, I plan to go into electrical engineering.
Excellent.
Awesome.
My name is Tyler Carnes. I'm also a senior at Glenelg High School. I'm looking to pursue mechanical engineering in college, but I'm also looking at a military pathway potentially.
Excellent.
Awesome.
Great idea. My daughter's in the military as well, and she's getting her degree as well. So they're very good. Okay. Tell us about your project.
So we're doing the Supply Pod Garage project. We have a presentation going through all our data and findings. So share that. Can you guys see it?
Yes.
All right. So as I said before, my name is Jonathan Polanski,
I'm Tyler Carnes.
and we're presenting the Supply Pod Garage project at Glenelg High School in Glenelg, Maryland, with our teacher, Raymond Gerstner.
So we researched our problem statement, and we found that lunar regolith is a common issue in the space atmosphere. It can clog equipment, destroy seals, and damage gear, leading to false readings with measurement equipment. We saw with Artemis 3 and future missions, they rely on a constant resupply of gear and food in the lunar environment. So we're looking to have a safe solution for these astronauts to resupply their gear on the lunar habitat.
So our first step in the research process was we decided to create a survey to gather data and receive opinions on what people thought on our problem. Our survey got 183 responses and it asked 3 major questions. The first one asked if regolith would be a minor issue, and we had 65.9% of people agree that it would not be. The second question asked if spacesuits restricting movement would impact the NASA missions, where we had 75.4% of people answer it would. And the third question asked how important a supply pod garage would be, and was answered on a scale of 1 to 5, 1 being not important and 5 being the most important. We had a majority of responses answer 4 and 5. Our next step was to research previous solutions taken at similar problems so that we could decide how we wanted to approach this problem. The first solution we researched was the BEAM, which stands for the Bigelow Expandable Activity Module. This was an inflatable ISS module, and despite it being collapsible and inflatable, it survives space conditions. The next solution we researched was the NASA Lunar Habitat, which is based in the Johnson Space Center. This gave us a really good idea on how we could potentially make some sort of rigid, secure, functional garage prototype. And the third solution we researched was the High Seas Habitat based in Hawaii. This habitat is in place to simulate the environment that would be on the lunar and Martian missions and has rigid interior modules.
Next, we'll go over our criteria and constraints that we found reviewing the presentation on our idea. First, we have our criteria. We have to protect the astronauts and gear from the lunar environment. It has to be completely airtight. It has to be resistant to the regolith wear. It has to have pressurization capabilities. Next are our constraints. It needs to be large enough to fit a scaled supply pod. It also must be collapsible and inflatable. And it must have regolith removable capabilities. So we'll have some instruments on board, such as the brush you were talking about earlier with the previous presentation, potentially using a horsehair material.
So after we defined our project requirements and went over previous solutions, we began brainstorming and creating concept sketches as to possibilities of how we can create our design. The first sketch here on the left was a full fabric garage and utilized an airtight zipper. This garage used telescopic poles as its support and had a separate loading bay and grate to remove excess regolith. The second design on the right had rigid collapsible walls. It was essentially planks with pieces of fabric sealed between them to allow for collapsibility for transport, yet a rigid, strong design once fully expanded. And this design also utilized an airtight zipper. Our third design on the left took a tent-style approach to the project with a separate pressurization chamber. This design would use telescopic poles as its support for the base, but we would use flexible aluminum rods to create a sturdy dome shape for the actual interior. And this design also utilized an airtight zipper. We also have insulation outside of the fabric to ensure that the inside of the garage stays around 21 degrees Celsius. The final design on the right took a foam style approach to the design. It was essentially a piece of foam sectioned into 4 separate squares, reinforced with aluminum tape. And our idea with this was that it would be foldable for transport, yet sturdy once fully expanded. This design utilized a heavy-duty door which would slide out into the side for sealability.
In addition to this, we had 3 other designs, and we took all 7 designs and we put them into a decision matrix to figure out which one would be best applicable for our design. We went over mass, cost, reliability, how airtight our design is, how well it manages dust, how much maintenance it would require, how scalable it is, how durable it is, and how transportable this will be on a spaceship. We found that our 7th design, the insulated fabric inflatable design, scored the highest. It had the best airtight, it managed dust the best, and it's very transportable with its inflatable design. So here's our in-depth analysis of solution 7. It's a durable design. It uses ripstop fabric, which would allow it to withstand regolith conditions, and have a reliable seal with airtight zippers. We're looking to use marine grade zippers for our prototype to simulate the airtight seal. It definitely meets our criteria that we reviewed earlier, and it would have a separate pressurization chamber, which will allow the astronauts to convert from the space pressure to the atmospheric pressure, which is inside where the supply pod containers would be.
So expanding on the pressurization chamber, we decided it was important to calculate how much time it would take for our scaled model to be pressurized. These calculations were made for our scaled model, assuming that the electronic air transferring system power would be scaled along with it. We used our target pressurization of about 10 psi, the gas constant of air, the average temperature would be, and the mass flow rate to determine that our scaled supply pod would take about 24.65 seconds to pressurize.
So we have our physical mock-up here. Originally, we had a cardboard design to simulate just the basic prototype. And then now we created our CAD design here. Let me see if I can angle this a little bit better for you. All right, so we have the roof here. And inside, we would have these dark lines in the corner here would simulate, I can also show you here. These would be our aluminum rods that would extend to create a rigid structure for the fabric to wrap around. And then these circles here below, which it's a better view here. This would be where our supply pods would sit and stay for storage purposes. And then on the front here, we would have one zipper in this compartment here to be the front face of the airlock. And then in the back here, there's also a second opening here where we have the second zipper to create a separate compartment here where the pressurization capabilities would allow the atmosphere to change from the space environment to the one atmosphere that is inside our habitat. Then here's our solution CAD. We get a little better view here in the light. So these light spots here are going to be where our supply pods are going to sit. Here's an exterior shell view. We'd have like a tent style design to run aluminum poles through the roof here and on these corners here to create a rigid structure. We have a front zipper design to create an airlock seal. And we have tool clips in the corners of these builds here. This will allow tools to be clipped, like such as a hammer or the horsehair brush to remove regolith.
So now that we have our final CAD created in our mockup, to create a correctly working design that was reliable, we need to use commercial off-the-shelf parts. We found a variety of parts we need from third-party and mainstream vendors. We would need to order two airtight zippers, one roll of ripstop fabric, one container of fabric glue, 5 pieces of zipper stoppers, 2 pounds of volcanic ash to simulate the regolith, 2 sets of telescopic poles, 4 pieces of aluminum bendable rods, 1 roll of insulation, and 2 one-way valves for the pressurization chamber. Our budget for this was $100, and we successfully stayed under at $84.51. Our testing plan here is outlined to make sure our design works reliably. We need to run it through a series of tests to make sure it meets all the design criteria. We're going to be testing for the sealability and airtight quality, the size of the design, the resistance to regolith, and the reliability of the seal. These tests have been chosen to make sure our design works as intended, reliably, and correctly. All right, thank you for listening. Do you have any questions?
Can we see your can you hold up your prototype? Let's talk from the
Yeah,
go ahead and stop sharing for the moment.
There you go. All right.
Okay. So so I'm going to drive up with the supply pod. Walk us through how it's going to get inside and how you're going to process it.
Okay. So we measured the opening here for the zippers to ensure that a supply pod would be able to fit through these with ease. That also accounts for the width of the astronaut and how much space they would take up in the opening. So we would have 2 airtight zippers in this back compartment here and the front compartment. This would allow the astronaut to unzip the first compartment, enter with the supply pod, and then zip up that front face. And then this compartment would then slowly pressurize using an air pump, and this would bring us to 1 atmosphere. And then this would allow the astronaut to, so this compartment back here always stays at 1 atmosphere.
Okay.
And the astronaut would unzip the second zipper here, enter into this compartment, and they would store the supply pod in the cylindrical holding spaces that we have for the supply pod.
Okay. So is it just the supply pod that's coming in? How are they moving the supply pod around?
So, we were doing research, and we plan to have this design compatible with the LTV. We want to have a separate area outside where the LTV can actually unload the supply pod and bring it to the garage before we bring it inside and unload it.
Okay. But what I mean is, are they rolling it like a great big ball? How are they moving it from one location to the next?
Oh, so yeah, essentially they would be rolling it because not only are they designed for the impact, so they'd be fine to roll, they also, since they're spherical or cylindrically shaped, it'd be really easy to roll it through the design and not have to carry the actual supply pod itself. But we did make the opening large enough to fit an astronaut around the supply pod. So if they decide it's something that needs to be more carefully taken in, or they want to carry it in, they have the possibility to do that too.
Okay. And you might think about ways, I mean, yes, it's a big ball, but imagine what it's like to try to push that around when you don't have you're used to. And so think about, should there be anything on the floor that would help them roll or manipulate that? And then now once I get it inside and I can take off my suit, how much room do you have around it? In one picture, it showed, that there was a whole lot of room. Remember, this is a building that has to fit inside of a rocket. So we've got to consider how much space you've got when it's all crumpled up and it's launching, in terms of how big it's going to be after it gets there. Okay, so I like where you're going with this. I think there's some great ideas. Now, you also show that your edges are very rectangular, and of course, that's where the pressure can be a problem. So you might want to think about how that's going to look if it's a little bit more rounded.
So for our design, we did have, so the compartment that stays at 1 atmosphere does have rectangular edges. Although the pressurization chamber, if I put the top on here, does have rounded edges just as a safety measure for when the pressure inside the compartment is changing, just to prevent issues with sharp corners.
And that's true, but just because it's not changing in pressure doesn't mean that you won't have problems with pressure pushing out of it. So you might want to round those as well. Okay?
Yeah.
All right.
Yeah. That's a good comment, because also any dirt or dust would accumulate in those corners and be hard to clean. We have that problem on the ISS now, actually. So
Okay. Flo, do you have some thoughts for him?
no, I like the design. I think they've taken care of the main issues, and I appreciate your work on this.
Thank you very
Thank
much.
you.
Thank you
Okay.
so much.
One more thought for you. So the habitat has to have the airlock of the porch, right? However, is it really necessary to have an airlock area for your garage? And what I mean is, if you can roll put your supply pod into the big garage without it being pressurized, is it really necessary to have the front pressurization area?
So essentially, the reason we decided to have the front pressurization area is to reduce the amount of time it would take to pressurize, because having a large open design like that would take a lot of time to pressurize, and we thought it wouldn't really be convenient or like feasible for it to take a long time to pressurize. So we figured that this design having its own separate, smaller pressurization area would make it more convenient for the astronauts to work with and unload the supply pod.
Okay, and that's a decent answer. All right. So now, when you mentioned that those entryways are going to be zippers. How did you want to arrange your zippers so that you're not rolling across as and damaging any of your zippers?
Yeah, you take it. So so essentially we have a curved like entryway design, and we were thinking once it's fully unzipped, we could possibly like roll it up and then have some sort of hook on the top to get it out of the way so it's not laying flat on the ground and you're not walking all over it, getting it dirty, possibly breaking something. So yeah, we plan to keep that out of the way.
Okay. And so part of what you're saying is you would zip from the bottom or from the top all the way down and back up and then roll it up. Is that correct?
Yeah.
Okay. And I'm all right with that. But even as I roll this thing in, I'm going to have a zipper on the bottom.
Mm-hmm.
And
Yeah.
so could that be damaged? Is there a way to protect it?
So we were thinking, this was in one of our concept sketches. We were thinking of having like a small ramp to get it up so it's not riding directly over the zipper or the ground of the entryway, and it lifts up to go over it. So that's one possibility of what we were thinking of. We have that in our CAD and our concept sketches. So yeah.
And I think that's a great idea. But it goes back again to my question about how are my astronauts manipulating this thing? So you can imagine if I've got a 6-foot diameter ball
Mhm.
and I'm trying to roll it over some kind of a hump that's protecting my zipper, that might be an issue. You see what I mean?
Mhm.
And so I don't expect you to have an answer for that right away, but it's something I want you to think about.
Yeah.
Okay?
Yeah. Thank you. Thank you for your feedback. Yeah.
So I think you guys have some great ideas, and I think that taking the zipper up and having the door kind of roll up, I think that's a great idea. And by the way, I think that the hatches are by far the most complex and difficult part of this, right?
Yeah, definitely.
Because you're trying to roll this thing in or you're trying to drive it in. And so, yeah, it's hard. And the other thing is, you pressurize this thing and now you're stretching that zipper. And so you have to really think about how strong can we make these zippers as well.
Yeah.
Okay. Good job, guys. I think you're attacking the problems the right way. How do you plan for the back of the garage to attach to the porch?
So we have we have it highlighted here.
I can see that.
Right there. Yeah, this is where the garage would actually attach to the main area so that once everything's unloaded, you could actually transfer it through and it's not just sitting in the garage.
Okay, very good. Now, I see that you've got this 3D printed at the moment, but you want it to be inflatable. Do you have a method? Is your next prototype going to show some of that?
So with the materials that we're looking to purchase, we're looking to create like a functional prototype using the fabric material that we're going to have. It would be airtight and it'd be able to be inflated.
I think that's great. And by the way, if you want to talk about inflatable and sewing these things up, don't be afraid to learn how to use a sewing machine.
Yeah.
Okay.
Yeah.
I'm not great with a sewing machine, but I can do it.
Yeah.
And hand stitching is okay too.
Yeah.
These are the kind of projects where if you really want to talk about making an inflatable, get a little bit of practice on that sewing machine so that you can show what. That way, you're much more knowledgeable about how this thing's going to be built. Excellent job, team.
Thank you. Thank you for your feedback.
I did have one question about testing. How are you going to test?
So
You had that chart, but it didn't explain how you were going to test for each of them.
It was in there, but it was a bit of a large phrase. So the way we're going to test for how airtight it is we want to use smoke. So that way we can actually see if there's any leakages anywhere and to ensure that it stays inside and that the whole design is completely airtight.
Good thinking, guys.
Yeah, that's good. So that would be airtight. How about, are you going to test it all for setting it up how long it takes to set it up or how difficult it is? And can you test for that at all? And taking it down even?
Yeah, we can absolutely test for that. We tried to make our design as simple as possible to put together since the base of it is fabric and you need to expand some poles and run them through. It's kind of like a tent. So, but yeah, we can definitely test for that, make sure it doesn't take too long to assemble and it can be done in spacesuits.
Yeah, right. And done in, Glenn, is there any other thing they should test for?
Well, this is one of those that's tough to test for. It's
Yeah.
part of it's the demonstration, right? So, for example, if you can make some portion of your prototype with cloth so that we can see how, it goes from being a ball into the final product, that's terrific.
Yeah.
But of course, when you do that, it's hard to see what's inside or things like that. And so it might be valuable to have, here's the one where we demonstrate how it might inflate, and then about what does it look like inside, or how do we attach and things like that.
Yeah.
So this is a complicated one because it's a scaled model, and it's really difficult for us to be able to test and demonstrate. It's more of, let me show as best as we can, right? So I like where you're going with this, guys. I think you got some great ideas. Keep this up.
Yeah.
Thank
Good
you.
job. Thank you so much.
Yeah, of course.
Awesome. You guys have a wonderful afternoon there. We appreciate your work. Thank
Yeah,
you.
of course. Yeah, have a good day.
You
All right,
too.
see you.
Okay.
Okay.
All right. So
Do we have somebody else?
now it's supposed to be Olympia.
Oh, okay.
And
be good.
but I don't see him on.
Okay.
So, and I did text him today, or last night actually, and he texted me back saying
Hey, Flo, how good
Yeah.
are you with sewing machine? Do you do much sewing?
I love sewing. I have a sewing machine right next to my 3D printer.
Uh-huh. And what kind of things do you sew most of the time? Because I think you've had some experience making some of the bags on occasion, haven't you?
Yeah, I'll show you. I made this.
Oh, did you? See? That's a nice looking cargo transfer bag. That's really good.
Yeah, but
Did you
I had help. I had
Yeah.
I had it at Johnson Space Center,
Yeah,
where
so you
we
did it
all
on
met.
you did it on one of the
Commercials.
machines
So
down here, right?
I actually do have my son has a commercial sewing machine that I use sometimes.
Oh, is that right? Okay.
Yeah,
Well, that sounds good.
yeah.
So
So I love
Okay.
sewing, but actually Stacy wanted me to do sewing initially, and
Uh-huh.
he put me on a sewing machine in the middle school at the time, and he said I made every mistake possible. That was the end of my sewing for him.
I'm pretty good at making all those mistakes too, I think. But, I like to sew, but it's a little bit of a struggle for me just because I don't do it often enough. You really have to have practice. And so I think it's great when students pick up the sewing because I think it makes a difference for them.
It
Okay.
does, and a lot of soft goods are necessary for space, so it's too
Well, I mean,
bad that
the whole thing is a soft goods thing.
yeah,
Okay.
yeah. So I'm checking my email, but I don't see Ryan. Andrew sent me an email, and he should be on now. Because oh wait, he shouldn't be on until 10:45. I have.
Oh, is that right?
Yeah, so we're early. So he's not coming on. 10:45 my time, which is 11:45 your time. So he should come on at 11:45. So we have more time.
Okay.
Actually.